in that case, we can move on to differential privacy. This is a concept that goes beyond federated learning. This is a concept that goes beyond deep learning, differential privacy. In 2006, Netflix put a recommendation system challenge, and they provided us, or provided the people on the internet participating in that challenge with data about movie reviews. And what they did was they anonymized the data. So they removed the name of the person who was writing the review. And they assumed that because they anonymized the data, nobody is going to know who wrote the review. And then some scientists wrote a paper, and what they did was they linked the Netflix data with IMDb data, which has the name of the review writers in it. This is called linkage attack. And they were able to reveal the identity of the people who wrote those reviews. You can do the same thing with public medical records. These are public, they are anonymized, and voter records. And then you can reveal the identity of the people. It is actually possible that you can reveal the identity of 87% of all of the Americans using only these three information: the zip code, their gender, and their birthday. Now you can reveal their identities, 87% of Americans. So what is the message? That privacy is very important. It is not enough to anonymize the data. And why privacy matters is because private data often contains sensitive information about one person, perhaps their medical record, perhaps how they voted, perhaps who they voted for, perhaps their social security number, tax status. There are actually these model inversion attacks these days that from a facial recognition system, you can recover the images that were used to train that facial recognition system. There are actually model inversion attacks on GPT type of models. And then you can reveal what type of data was used. Not all of them, but a fraction of them. It turns out that each time that you interact with a data point, you're revealing some information about it. And that interaction could be as simple as querying a data point from a SQL database. So the idea is to minimize the number of interactions that you have with your data to preserve their privacy. Or if you have to interact with your data a lot of times, like going through epochs of your training and then keep interacting with your data, we train our deep learning models on public data, but we can train them on private data, perhaps from your customers. And then you want to protect their privacy. So each time that you touch a data point, you're revealing some information about it, and you want to make that training process preserve as much privacy as possible. And this is exactly what I just mentioned. Each time that you access a data, there is potential for privacy leakage. And then we are going to be talking about privacy preserving learning. When it came to federated learning, preserving the privacy of those data is even more important. And there are ways to make things rigorous, have rigorous definition for privacy, especially differential privacy. This goes beyond deep learning. This is for even touching a data point, querying it, operations as simple as that, let alone training a deep neural network using it. A learning algorithm, for instance, stochastic gradient descent, is said to be differentially private if not a single data point matters too much. What do I mean? If you add that data point, modify it or remove it from your set of training examples, it doesn't matter. It means that it is guaranteed not to result in a statistically significant model. So imagine you have a data set, you add a new data point to it, that's going to give you a second data set. You do your training on them, on these two data sets, and then you're going to use it to do predictions. You want those predictions not to be different. You want these two models not to be different, or in a statistical sense. Think of this example in your mind. It's going to help you understand differential privacy. And why do you work with log ratios? Why do you look at the outcome of a model. Let's say you have a data set of people having COVID or being tested positive for COVID or not. You have a second data set, which is basically the first data set plus an additional observation about a person, perhaps John. So you have a data set, you have another data set, which is the first data set plus a new observation about John. You train two models. You take that model, it's a classification type of model, whether you have COVID or you don't have COVID. You apply it on data from John. The first model trained on the first data set is going to give you a probability of 0.55. The second model trained on the data set which included John or John's record is going to give you an outcome, a probability of having COVID of 0.57. So 0.55, 0.57, they are not that different. And then you cannot say whether John had COVID or not. This is called plausible deniability. John can simply deny that they have COVID. On the other side, if the first model is giving you 0.55 as the probability of John having COVID, the second model, which includes the John's record, which is trained on a data set including John's record, is giving you 0.85. Suddenly the probability increased by a lot. Your model is suddenly more confident. And then you can be much more confident that John has COVID. And you're revealing some information about him. So is this example clear? Because I'm going to refer to it back. And this is to prove the concept that each time that you touch a data point, include it, modify it, remove it, you're revealing something. You're revealing some information. One way to deal with that, with John's story, is to sometimes randomize. Whenever you're adding a new record to your data set, sometimes include something random. Perhaps flip a coin and then say John has COVID, and in fact he didn't. And sometimes do the opposite for somebody else. Introduce randomness. And then it's going to become harder to reveal the data or reveal identities. You are going to use the same concept of randomization when you're training. When you're training a deep neural network, you're going to be touching your data all the time through your epochs. You have a loss function. You're going to compute the gradients per each observation of your loss function. And then what you would do, forget about clipping and adding noise. You would descend in the direction of the parameters or in the direction of reducing the loss or in the direction of your gradients. And from these gradient updates and some model inversion attacks, or perhaps some other process that we don't know, you can extract information about the data. Knowing the gradients, you can extract information about the data. Okay, if that's the case, if by looking at the gradients, we can extract information, perhaps one way to increase privacy of our data is to add noise to the gradient. And this is what you do here. You add noise to your gradients. You keep sampling random numbers, add them to your gradient, and then that's going to give you an approximation of your gradient update. But then you want these gradients and these noise that you're adding to be of the same scale as your gradients. That's why you clip your gradients first. And that's going to give you your scale. Gradient clipping, we used to use it when we had to train recurrent neural networks. So the idea is not new. And at that time, we were using them to avoid vanishing or exploding gradient problems. We are going to be using it here to control the magnitude of your gradients and then to control the magnitude of your noise. Let's see what happens. If the norm of your gradient is less than C, this number is less than 1, so the maximum is going to be 1, and then your gradient is going to be itself. So if the norm of the gradient is small enough, you're going to be working with your gradients. If it is bigger than C, this is going to dominate. The maximum is going to be the second term. You're going to be dividing the gradient by its norm. It's going to have a norm of 1, and then you're multiplying by C. So the norm of your gradients is going to be C. In the cases that they're bigger than the clip parameter. And this is clipping. So G bar is not going to have a norm bigger than C. And C is the one that is going to determine the size of the noise that you're adding in addition to another hyperparameter, sigma. Okay, perfect. Now you can play around with C and sigma. For instance, if sigma is 0, you are working with true gradients. And if you work with true gradients, in the end, you're going to get a very good model. Hopefully, if the training process is a nice one, you're going to end up with a very good model. But as you add noise, you're reducing the quality of your model. So there is going to be this trade-off between how accurate your model is going to be and how much you want to preserve the privacy. If you want to preserve the privacy a lot, you keep adding a lot of noise, and then your model is going to end up being less accurate, but you're preserving the privacy of the data throughout the training. And you can go the reverse route. So you have these knobs to tune, sigma and C squared, to balance the trade-off between accuracy and privacy. And if you want to have a metric or have an estimate on how much privacy did the entire process lose, you want to have an upper bound on it. And if you have that upper bound, you can set these two hyperparameters using that upper bound. So that upper bound is going to be your evaluation metric. That is going to help you set your hyperparameters in the training process. So your problem is now going to turn into putting upper bounds on how much privacy the training process is going to lose. It is a fact that each time that you're touching the data, you're going to lose privacy. You're revealing something about your data. Not touching the data is not an option. So you're going to be using your data, but then you want to put an upper bound on it. And as soon as you put an upper bound, you can tune these hyperparameters not to exceed that bound. Okay, where does that come from? This epsilon and delta. This is about any mechanism. It's not only about this mechanism of training or privacy preserving stochastic gradient descent. It is about any mechanism each time that you touch a data point. So this is a generic definition. Any randomized mechanism, which could be a simple query of your data set, is going to be epsilon delta differential private if this relationship holds for any two adjacent data. What is that? Why? Where is this formula coming from? Where are you getting the exponential? Why do you need epsilon? Where are the probabilities coming from? Let's go back to our John story. You had a data set. You had another data set with John included. You use those two to train a model. In this case, that's your randomized mechanism. And then you were querying your model. You were saying, what is the probability that John has COVID? So you had a probability of John having COVID. So S is the outcome of having COVID. This is the probability of having that. This is the probability of having COVID in the case that you use a different data set to train your model. And then if this probability was large or if it was too small, you were revealing something about John having COVID or not. That's why you're going to be working with the log of the probability ratios. And let's take the exponential here. And let's say you want to bound this by epsilon. You take exponential, it's going to be the probability of the numerator. It's going to be less than or equal to e to the power epsilon, the probability that is showing up in the denominator. And that's where this formula is coming from. And this is where the epsilon is coming from. You want to put a bound on the log of the probability ratios. The smaller is epsilon, the less you're revealing about your data point. And then you want to do this up until the margin for you to be able to prove upper bounds. Okay, first thing first, the question is, you gave us an algorithm, differentially private stochastic gradient descent. Is it actually privacy preserving? The answer is yes. It is going to be privacy preserving with these epsilon and delta as the upper bounds. And then you can use that to set your sigma, for instance, which is one of these hyperparameters here. Okay? Don't worry about the details of that. The answer is yes. This algorithm is privacy preserving to some extent. You're going to be revealing something about the data in the end. Now the question is, how much do you reveal? The theorem also gives you tight upper bounds. The more epochs you go, the more you're touching your data points, the more you're revealing about your data. So epsilon is going to grow. This is a tight upper bound. It means that you can trust it more than a looser upper bound. If you work with that as your upper bound, you are being very pessimistic about your training process. You are saying that my training process is revealing too much information, and therefore you're going to be adding more noise, and therefore you're going to have a worse model. It's going to be less accurate. So having a tighter upper bound is going to help you set these parameters, hyperparameters, more intelligently, and don't overthink your problem. And that's coming, these upper bounds are coming from some moment analysis. You look at the mean, you look at the variance, you look at the higher moments, and then you're putting the upper bound. So if you're interested in the math, definitely take a look at that paper. It's a very good one. But in the end, that's just a proof, and that's giving you a tight upper bound. Okay, so far so good. As I mentioned, there is going to be this trade-off between accuracy and privacy. For instance, on MNIST data, you can achieve 90%, 95%, 97% test accuracy. For the 90%, your epsilon is going to be 0.5, which means that you are more privacy preserving. You're revealing less about your data, but then you're less accurate. If your epsilon is 2, it's bigger than 0.5. It means that you're revealing more about your data, but then your model is going to be more accurate, etc. That's why having these upper bounds are important. Having epsilon is important. That's an estimate of how much privacy you lost. How much did you reveal about your data? Let's go back to our backdoor federated learning story, that you can actually backdoor federated learning. It turns out that using this algorithm, privacy preserving stochastic gradient descent, is going to help. And by the way, this algorithm is already implemented for you in TensorFlow or PyTorch. You can also implement it on your own. It's not that hard. And all you need to do in PyTorch and TensorFlow, if you are working with private data, if you go and work in a company later on, you're going to be using this optimizer rather than plain vanilla stochastic gradient descent, because you need to preserve the privacy of your data or your customers. It turns out that this algorithm helps, but then there is a cost to it, which might be a good thing, which might be a bad thing, that if you use differentially private stochastic gradient descent, you are going to be preserving more privacy of your users, but at the same time, you are going to be serving them less accurate models. So it is a solution to the backdoor attack, but it's not a perfect solution. And there might be a better solution to solve that problem. I think I'm going to stop here. And with that, we are concluding the federated learning section of the course. For those of you who have questions, I'll be around.